Hey, what's up, guys? This is Sheng here. So today, let's take a look at LeetCode problem number 1489. Find critical and pseudo-critical edges in minimal spanning tree. So this one is a very interesting graph problem. Okay, so you're given like a weighted, undirected, connected graph, right? With n vertices, number from 0 to n minus 1, and an array of edges where the each edge has like starting point, start, end, and the weight. This is pretty standard, right? And then it asks you to find the critical and the pseudo-critical edges in the minimal spanning tree. So there are like a few terminologies we need to be clear first, right? So first, what is the minimum spanning tree? Which is in short, it's a MST. So a minimum spanning tree is a subset of the graph's edges, right? That connects all the vertices without circle, right? And with the minimum possible total edge weight. Okay. So here, I mean, for those who are not familiar with the MST, which is the minimal spanning tree, if we have like a lot of nodes and there are like a bunch of edges, right? Yeah, I'm just trying to write a bunch of edges here, and each edge has like a weight, right? So a tree, of course, right? A tree is something. A tree is a subset of the graph, of course, right? I mean, a tree means what? A tree means that the edge. So the edge equals to the node minus one, because a tree cannot have a circle, right? If we have like the edge greater than n minus one, then we know it has to have a circle. I think that's one of the way we can detect a circle. Okay, and among all those kind of tree structures, right? Because with this kind of many edges, right, we can have like multiple tree, and the minimum spanning tree is a tree that has the smallest possible weight, and obviously there could be multiple MST as long as they all have the same minimum total weight, right? And then it's this critical and pseudo-critical edges. So for the critical edges, this one is easier to understand, which means that MST edge, this edge is critical. If you delete this edge, the total weight. I mean, if you delete this edge, basically, if you don't include this edge from your from spanning tree, the weight, the smallest weight you can get is greater than the minimum one. Then this edge will be the critical edge, right? Oh, and actually, there's like a implicit condition here. If by removing this edge, you will not be able to form like a graph that connected all the vertices, this edge will also be a critical edge. So what does this mean? It means that let's say there's like this edge, this like graph, right? Okay, here there's like this graph here. So this edge, this one, it doesn't matter what's the weight on it. This one is definitely a critical edge, because if we remove this edge, there's no way we can form like a minimum spanning tree, right, for all the vertices. So this is the implicit condition here. We have to be careful. All right. Okay, so now we have talked about what the critical edges is. Basically, if you remove that, if you exclude this edge, and if you and no matter how how you try to form like a minimal spanning tree, and you always get like the a bigger weight, and then this edge is a critical one. Okay, and so for how about the pseudo-critical one? So the pseudo-critical one is a little bit tricky here. Basically, the pseudo-critical one is the pseudo-critical edge is that it can appear in some minimal spanning tree, but not all of them. Okay, so what does it mean? It means that if you remove it from the if you exclude basically if you exclude from the minimum from the minimal spanning tree, we can still get uh, the same minimum value, the minimum weight. Then this edge will be a pseudo critical one. So how about some examples, right? So for example, we have this kind of map here, right? Sorry, not map, graph. And as you guys can see, the minimum spanning tree, we could have like 4 minimum spanning tree. All these 4 minimum spanning tree, they all have the same weight, which is 7, right? And as you guys can see, so the answer for this one is what? Basically, edge 0 and 1, they are critical. They're critical edges, and the rest are pseudo-critical. And why is that? Because, let's say if we remove this edge, right? If we remove this edge, no matter how we try to form like a tree, the total weight will always be greater than 7. Same thing for this one, right? You guys can try it, okay? But in terms of the pseudo critical one are the 2, 3, 4, and 5. So which means that if we remove this one, we can still form like a minimum spanning tree, right? With the same weight, which is 7. So basically, that's how this problem was described, right? Cool. And to solve this problem, we need some basic knowledge about how can we form a minimum spanning tree, right? So we do it by using a union find. Okay, so that's a very classic, solution code, for minimum spanning tree. Basically, we sort the edges by the weight from the smallest to the biggest, and then basically we greedily pick the edges from the smallest weight, and we try to union them together, right? And by the end, we finish the union. The all the edges we have been union together will be one of the minimum spanning tree. So that's how we do that, right? And then obviously, once we have that minimum value, right, by utilizing that union find algorithm, to find the critical one, it's pretty straightforward, right? Basically, we'll try to exclude that edge from, we'll try to exclude that edge, and then we'll apply and then we'll apply that same union find solution, and then we'll try to get a new minimum. We'll try to get a new weight, and if that weight is greater than the minimum one, or like I said, or we cannot form a proper a graph, a spinning tree, right? A spanning tree, and then this edge is a critical one. And then how about the second one, right? And in regards the pseudo critical edge, we can do something like this. So basically, if the first condition is this, right? So if the weight, okay, I'm using W. If the weight is greater than the minimum weight, okay, right? Or it's not like, or not a graph, okay, or not a tree, right? Or not a tree, and then this one, right? Then this edge is like a critical edge. I use CE to represent the critical edge, right? Okay, so that's the first condition, right? Second one is the else, right? So remember, since we already have this kind of minimum weight, right? Minimum weight across all the trees, right? So which means that re regardless which combination what kind of edges we choose, the weight will always be either equal to this one or greater than this one, right? So what is else? Since we already covered the cases when the weight is greater than this one, so the else means the weight is similar. The weight is equal to the minimum weight, right? So in this case, okay, so the precondition is like this. So this one is like by after, right? After excluding, right? After excluding edge I, okay? After excluding the edge I, if the weight is greater than this one, no, so this edge basically I is the critical edge, right? Else what? Else means that if after excluding this edge, the weight is equal to this one, then there are like uh two pos two possibilities here. So the first one is that of course this edge is one of the pseudo-critical one, right? And the second one is what? Second one is that this this edge this edge will not be should not be included in any of the minimum spanning tree. So which means that let's say if we have a bunch of uh the edges, right? Doesn't really matter what the edge is. So let's say there is an edge. So this edge has like weight 10. All the other has 1, 2, 3, 1, 2, 1, something like that. So obviously, by excluding this 10, right? I mean, we can still get this minimum weight, but this 10 should never appear in any of the minimum spanning tree. So which means that when it comes down to this else condition here, it means that we have two conditions. So the first one is that I does not, right, does not belong to any MST, right? So if that's the case, so if I does not belong to any the MST, obviously this I should not be a pseudo-critical edges, right? Because remember the definition for the pseudo-critical edges is that this edge belongs to some of MST, but not all. Okay, so again, MST means that it has to be the weight has to be equal to the minimum, right? So okay, so and then the second one, of course, the second one is that I is a pseudo is a pseudo PCE. I use PCE to represent pseudo critical edge. Okay, so which means that when it comes down to the else condition here, we also need to check. We have these two conditions. So which means that we want to check if we force the solution to include this current edge, right? And then if we get like a bigger weight, then we know, okay, so this I does not belong to any of the MST, right? Because I think I'm repeating myself, right? Because because we have a minimum weight there already fixed, right? So if we include this edge and we get like a greater one, it means that this edge, for example, this 10, does not belong to any of the MST, and we can simply use that to verify if this edge is a pseudo-critical edge or not. And that's all the logic here. And as you guys can see, since we're going to run that, the union find solution multiple times, and it's better for us to create like a separate class, right, so that we can create multiple instances to run multiple like union find solution. Okay, cool. So let's start coding then. Like I said, we're going to create like a separate class for the union find. Okay, and all right. So here we have init, right? We have self, and we have n, right? Because we need that. So for the union find, I'm not going to talk too much details about how should we implement the union find, right? Basically, we need a parent, going to be a list of the range of n, right? At the beginning, every node has a parent equals to itself. And then we're going to have like two methods for the union find. Of course, the first one is find. It's going to be an x. So the way we're implementing is, whenever the x does not equals to itself, sorry, the parent of the x is not of the value itself, then we know we need to go back, right? We need to keep looking forward, keep looking to the looking for the parent. That's how we do this. Parent.x equals to self.find self.parents.x. Okay, and then we return this self.parents.x. So here, this is like a technique. It's called path compression. So which means that so the idea of the find here is it's to find the root for this for this x, right? And like I said, so let's say this is the root, right? And if we have like a lot of child nodes who has the same root here, let's say for example this one is x, right? If we don't compress the path here, so every time we try to find the root for this x, we have to go all the way back to the root. It's a linear scan, right? But so this kind of recursion call, what it does is that after the first query, this x will be moving to here instead of at the end of this kind of tree structure. That's how this kind of recursion works. So basically, only the first time it will cost a linear time. The next time it will only cost O1 time. Okay, so a little bit about this find, right? And for the union is like pretty straightforward. So we have a x and y, right? And then for the root one, it's going to be the self.find x. So to union a two node, we first get each of the nodes like root or the parent, and then we only union when they are different, right? So R2, then we do a union. Self.parent.R2 equals to R1, right? So that's how we do the union. Actually, to make this union find complete, the complete union find algorithm should also include like a ranking for each of the root. So which means that every time when we assign the parents, we can either, as you guys can see, we can either assign R1 to assign R2 to R1, or we can also assign R1 to R2, right? Either way is fine. But which way should we use? Basically, if we have like a ranking here, we should always assign the root has a smaller ranking to the root has a larger ranking, so that this kind of can guarantee us the tree is like kind of balanced. We won't take too much time to do the union and find. But for our case, I simply remove that ranking parameter to make this algorithm a little bit simpler. Yeah, and okay, so that's basically the union find code here. Okay, and so let's add a few more stuff here. Okay, so first, since we need to get the weight here, right? We need to get the total weight of after do this union find. So we can have introduce a second parameter or a field called weight equals to 0. Okay. So and every time, right? Every time when we do a union, we're gonna pass like a third parameters called weight. So whenever we include this edge, right, we simply add this weight to the total weight. Okay, that's that. All right. Okay, so I think we can leave this one for now, and we can add more stuff later on. So let's try to use this one to find the minimums, find the weight for the minimum spanning tree. So like I said, first we're gonna sort these edges by the weight, right? And since we're going to return the indices of the edges, we're going to also store. We're gonna add the original index to this list. So which means that since we're going to sort by the weight, I'm going to put the weight at the first element. It's going to be a weight, and we have A, B, and I, right? And I, okay. Then for I, A, B, W, right? Enumerate edges, right? So I just did a little massage, right, to this one, and then we just simply sort this one, okay. And then so here, okay, step one, right? Step one, find minimum weight for MST. Actually, not mean find weight for MST. Okay. So we have so we need to have a like union find instance. So union find n, right? For W A B I, right? In range, actually we don't in edges. So actually we don't need this I here. We can just use it like this one. Underscore, right? We do a union find one dot union A and B and W. Okay. And then the minimum weight, right? So we have minimum weight is going to union find one dot weight, right? So after doing this kind of union find, this weight will give us the weight for the minimum for the MST, which is this one. Okay. Now let's find the critical edge and pseudo-critical edge. So for the critical edge, I use the CE. It's going to be a list, right? And then the pseudo-critical edge is another also like list. So here, step 2, right? Try to exclude each edge, right? And then run the MST algorithm, right? So for I in range of m, maybe, okay. So let's do a m equals to length of the edges, right? So for each of the edge, we're trying to exclude, right? We're going to run like union find. That's why I'm going to have a union find 2. In this case, going to be a same thing, union find n, right? And then for j in range m, okay. So if the I is equal to j, right, we simply continue, which means we are like excluding this edge. Otherwise, we'll do a union find. We'll do a union find again, right? So we have a W, A, B, and this one equals the edges of I, right? Sorry, edges of J. Okay. Union find 2 dot union, right, of A, B, and W. Okay. So now, like I said, if the union find 2 dot weight, right, not union find 2 dot weight, this one is greater than the minimum of weight, then we know, okay, so this edge is a critical edge, right? So this critical that append dot I, actually not this I, because we need the original index, which is the edges, right? Edges dot I dot 3, right? That's the original index. So like I said, here, this is not the only condition. We also need to know, by excluding this edge, if we cannot form a proper tree, then this one is also like a critical edge, right? So how can we check that? Remember, so when I say, for a tree, for a tree to include all the vertices, let's say the vertices is n, right? So the edges has to be the same as, has to equal to n minus 1. That's a condition to form a tree. So which means we can also have like an edge count, right, in this union find class. So every time when we include an edge, we simply just increase this counter by 1. Okay. And then here we just check, right? Or the UF2 dot edge count is smaller than the n minus 1. And then we know, okay, this one is also like a critical one. So basically, if the new weight, right, is greater than the minimum weight, right, or we cannot form a tree, right, a proper tree which contains, right, all the nodes, right, then this one is like a critical one. Else, right? So else, like I said, we have two conditions here. Else means this weight is the same as minimum weight. Then we need to check, right? Need to check if the edge the edge I, right? If the edge I should not belong to any MST, right? So how can we check that? Like I said, we force to include edge I and then run MST algorithm again, right? So then let's do it, right? So which means we need another like union find, right? So that's why I create this class, right? So I have a union find of n again, right? So we have, so now to force include that one, of course, we simply just do a union find, right? We do a W, A, B, this one equals the edges of I, right? Because this is the edge we're trying to force to include. And we simply do a union find 3 dot union, okay, of A, B, and W, right? Because at the beginning, everything, there's nothing union together. That's why when we try to union this edge, it will definitely be union, right? And then we just do another, we just run like algorithm followed continually, right? After this one, so we have J in the, I'm going to use a J in the range of M, right? So again, we're going to have a M, W, A, B, and this one, right, equals the edges of J, okay? Then we're going to run union 3 dot union dot A and B, W, okay? So now if we check if the union 3 dot weight is equal to the minimum of weight, then what? Then this one, then this edge, this this edge is a pseudo-critical one. Append dot edges I dot 3. Yep. So and then return the CE and the PCE. That's it. Yeah, I think that's it. Right. Let's run the code real quick here. I think there must be a typo here. Union find 3 union. Okay. Okay, accept it. Right. If I run it. Yeah. Cool. So it's passed. Right. So and the time complexity, space complexity. So we have like this sorting. It's nothing. I think because here's the real time complexity. So we have m, right? So obviously we have a nested for loop here. So this is going to be a m square, right? And so we have a m square, and here is like also a for loop here. But they are like parallel. Yeah. So I think the time complexity will be a m squared because, like I said, each of the operation in the union find, uh, either like find or union, we can treat them as O1 time complexity. That's why the total time complexity is going to be m squared, right? Where the m is the total, is the edges, right? Cool. And space complexity is going to be O of m, right? Because we have this kind of edges. And yep. So that's it, right? I mean, it's a pretty tricky one. Actually, it requires you to have many small pieces, the small knowledge pieces, and you need to stitch them together. First is like what is MST? How can we get a MST weight, right? The minimum weight. And then from there, we have to run a bunch of for each of the edge, right? After excluding it, we run this MST again, and then if this after that, if the weight is greater than the minimum weight, or this one's pretty tricky, or this one will not form a proper tree, and then this one is a critical one, else. So actually, this one is even trickier. Else, this one, this one it means that by excluding this current edge, we can still get the minimum spinning, the minimum weight, right? But to be able to check if this edge is a pseudo-critical one, we have to basically force to include this one because there are like two cases here. Either this edge is the pseudo-critical one, or this edge should not be included in any of the MST, right? So the way we're checking is that if we force to include this edge, and if the weight is greater, than the minimum one, then we know this one is not like pseudo-critical edge, right? And we only include this one when the weight is the same as the minimum weight. And yep, that's it. Cool. I think I'll just stop here then. All right. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.